But the way I draw it in space here is just to give you, to emphasize the different areas of the problem. But in reality, it's a one-dimensional problem. So a rocket's going to take off from the ground, from rest. It's going to be under power of the engine for some period of time. I think in this case it's 40 seconds. At which point, after the engine shuts off, it's now a projectile. So under projectile motion, it's going to go up and stop at some point, right? And then it's going to fall, right? And it's going to fall to the ground, back to the ground. Okay? Now, in these different situations, here under thrust, its acceleration is going to be it's a fight basically between the thrust and the gravity. Here it's going to be gravity, so we're moving in this direction, and gravity is pulling down in the opposite direction of motion. And then here we have the force of gravity going down, and the motion is going down. So literally what it means is that my acceleration value or direction is going to change in each one of these sections. So when that happens, it's best to break this up into three separate problems. So let's call this problem 1, right? Problem 2, and problem 3, right? In this way, we treat it as three separate problems, and it'll make life a little bit easier for us. So when the rocket is flying in this problem 1, let's start with problem 1, right? The rocket is flying in problem 1, we have the force of gravity is going down, right? We also have the force of thrust going up. Now we're neglecting air resistance, and if we're neglecting air resistance, which is sum of all forces, here's our free body diagram, step A, whatever. Step B is going to be sum of all forces. So if we assume the direction of motion is this way, and the force of thrust is this way, and gravity is down, that means we're going to do force of thrust minus the force of gravity equals mass times acceleration according to Newton's second law. So we wrote the sum of forces, and now the next step is to solve for the acceleration. So we're just going to divide both sides by m. So the acceleration then equals force of thrust minus the force of gravity over m. In this case, the thrust was 400 newtons, right?
Yeah.
And the force of gravity is the mass times the acceleration of gravity is 25 kilograms is the mass. So the acceleration of gravity is 9.8 divided by the 25 kilograms is the mass. Okay? And I think when you guys did this last time, you said it was 6.2 meters per second squared is what you guys came up with last time when you guys did the calculator. But I urge you to check the numbers yourself with the calculator. So step A is free body diagram, step B is sum of all forces, step C is acceleration, and then the next step is the equations of motion, right? So let's do the equations of motion. So in this case we have V final because V initial plus AT, and we have Y final plus Y initial plus V initial T. It's 1/2 AT squared. Again, these equations are given to you. So looking at this equation, we know that the burn on the engine is 40 seconds. So we know this time. We know the acceleration is right there. We know the initial speed is 0, right? And if we consider this location as the ground, we can also say that the initial position was 0. So in this equation, we know everything. We can solve V final, right? So therefore, V final, in this case, is going to be A times T, and A is 6.2. Actually, let me just write A times T, right? Which is 6.2 times time, which is 40 seconds. Yeah. So V final is 248 meters per second. Okay. So that's the first question to ask: is what is the final speed here? Right. And we should know what the final height is at this point. We just found the final speed at this point, which is the first part of the question. Now we can find out what the height is. The height, Y final, is going to be 1/2 AT squared, okay? Which in this case, is 1/2 times 6.2 times 40 squared, okay? So Y final, what was it, 4896, I think? I don't remember.
It's 4960.
What?
4960.
4960?
Yeah.
4960, like that?
Yeah.
Okay. That's what you wrote. But you should still calculate it, okay? I mean, in a calculator, don't, because the numbers will change, so. Now, just out of curiosity, what happens if the acceleration is negative? Here. I mean, just out of curiosity, if your force of gravity is bigger than your force of thrust, what's gonna happen?
It wouldn't go up.
Nothing, it'll just sit there all day, right? Just make a bunch of heat. Probably catch everything on fire, okay? So that's a good point, right? Is the first thing you want to verify is if this is a positive number. Could be a problem otherwise, right? One time I did a test and I chose the wrong numbers for the thrust and the mass and everything, and then they were like, wait a second, I'm getting a negative acceleration. And you know, the ones that didn't catch it, of course, got problem points out, and the ones who caught it, I gave them extra credit. So at this point, we know now, we know everything about this problem one. So problem one is done now, right? Part one is done now. So now we can focus on part two. In part two, right, we have a few things. First is, we're starting from this point and going to that point. At this point, we now know what our V0 is, and we now know what our Y0 is, because that becomes our Y final and V final from the previous section, okay? We know that. And also we know what? We know what the final speed here is, don't we?
Yep.
Yeah, because we know at some point it's going to stop and they go down, so that speed is 0. So we know a lot of things. The forces acting on this guy are just now the force of gravity, neglecting air resistance. So force of gravity is the only thing acting on this bad boy. So if that's the case, we do the sum of forces. No, just like step 1, step 2, step 3, and so on. So we just rinse and repeat over and over again, right? So this is going to be sum of all forces. In this case, the direction of motion is this way. The force of gravity is down, so this would be minus Fg, right, equals ma. And I'm going to solve for acceleration, so this is going to be acceleration is equal to minus Fg over m. And Fg is mass times the acceleration, right, so it's going to be minus g, right? Because it's mass times the acceleration of gravity over m, so the m's cancel. So we found the acceleration, so we did here. You know, the acceleration is g. The next step is, you know, we're going to put in the equations of motion, right? So we have V final plus V initial plus AT, right? And we have Y final plus Y initial plus V initial time plus 1/2 AT squared. Of course, A equals negative G, so I can just replace this, right? I'll just write it here. And this one here is going to be Y final V0T minus 1/2 G squared. So these are our equations of motion right now as we got them. Now what do we know? On this equation, we know what? We know V final, right? We know V initial. We know G, but we don't know time. So we can use this equation to find time. In this equation, we know Y initial, right? We don't know Y final. We know V initial. We don't know time. So there's multiple things we don't know here. So it's better to use this one first. Okay, so if I do this, this is equal to 0. V0 minus GT. And again, we're going to bring this guy over. Okay, so that means we have V0 equals GT. That means T equals V0 over G. That's my time. Okay. In this case, how far down can I go before I lose you guys? T equals 248 divided by 9.8. Right? I don't know, it's like, what was it, 25.3 seconds? Yeah. Okay, so it took 25.3 seconds to go from here to there. That's what we just found out. Okay? Now that we know the time, we can plug it into this guy. So Y final equals this is Y0 now, which is the 4960 plus V0 is a 248, right? 248 times is 25.3 seconds, right? Minus 1/2 G, which is 9.8, times the time squared, which is this squared, right? Which is the 25.3 end of the day, this is just the difference of this half, so if you have that on the calculator, you can just do that. So it's gonna be half of this, so it's 4960, basically it's 4960 plus 1/2 248 times 25.3. That's what it's gonna end up being, so whatever you guys get in your calculator. $80.98. Is that you looked up or you calculated?
We got that yesterday.
You looked it up. Okay, I'm just saying. Okay. So 89.8 meters. Okay, so almost 10 kilometers. So right now we know the maximum height. Right, we just found the maximum height, which is one of the questions it was asking. So this maximum height here. This is H max. Okay, we just found it. So that's this guy. Okay. Okay, so that's the maximum height. The only thing we have left now to find, we have the time here and the time here. The only thing we have left is the time of the fall, right? So part three, right, is going to be now doing this part of the problem. So if we look at this body here, force of gravity is acting like this, but it's also moving in this direction, right? So this is my free body diagram, step 1. Step 2 is my sum of my forces, right? In this case, gravity is going with acceleration, so it'll be a force of gravity plus mass times acceleration. Okay, so if I solve this, then I get A equals the force of gravity over M, which equals G. Okay, because, right, because the force of gravity equals M times G, right? So the M's cancel. And then the next step is to plug it in the equation of motion. So we have V final plus V initial plus AT. We don't really care about the speed when it comes down. And also this equation doesn't help us much because we don't know the time and we don't know the final speed, right? Even if we know V0 and A, we still can't really solve this problem because we have two unknowns. So instead, let's look at the Y final minus Y initial. This is the distance it's going to fall, right? Because V0t is 1/2 AT squared, okay? So, the distance it's going to fall here is the same as this position minus this position, right? So, it's the distance it's going to fall, which is what? Which is our H max, which is this guy right here, right? Yeah? This is the distance it has to fall. So, I'm going to call this H max. This is V0. Now, V0 here is what? It's 0, right? It started off at 0 speed. You remember, we said this V final here is 0 for this part of the problem. But now it's starting here. So if it was 0, then it started at 0, right? Yeah? Okay, so that means V0 equals 0, V0 equals 0 here. So that's 1/2. A is equal to G. That's time squared. We know this, so we can find that, right? So multiply by 2 on the other side, 2. I can tell by your looks you guys are not happy right now. Where did I lose you?
Wouldn't VF equal to 0? Because
No. In this case, this is V0 and this is VF here, right?
right,
For this part. So VF will be 0.
because it would stop when it.
Well, it's not because it hits the ground, but the instant before it stops, it's moving pretty fast.
Okay.
So it's not really 0. Okay? Like in the soccer ball, when we did this, the initial speed here, V0 here, is going to be equal to the V0 there. That's the soccer ball in projectile motion. So if we did it from here to here, this speed here, V0 here, would be V0 there, or V final here. For this guy, right? Coming back down, it'd be the same speed. But this is because it's under thrust. We don't have an initial speed here. So all this from this point down is accelerating. So it's going to be quite significant. Okay? Okay. So now we solve this for time. So time squared equals 2h over g. That means t equals square root of 2h over g. And we have it, right? I said?
Yeah.
40.7 seconds. Okay, so now that we know the time, we're done, right? Because we know this is 40 seconds of the rocket burn, right? This part is 25.3 seconds, right? And then this part right here is 40.7. So the total time of flight, okay, is 40 plus 25.3 plus 40.7, which is what, 106 seconds. So that's the last thing it's asking. Yes, it first says, you know, how fast is it going when the rocket engine stops? What's its maximum height? And then how long before it hits the ground? Okay? And as we said, you know, free body diagram, sum of forces, find the acceleration, plug in the equations, that's every step. That's all you're doing. So if you look at it as this is just the problem here, that's not too bad, right? I mean, it's not really that hard. Just recognizing you have to break into three problems, that comes from experience.
I'm not getting the same answer for Wi-Fi now.
Okay, so we have a block sitting on a platform, and there's a force pulling on the block, right? Let's call it pull. Let's call it FP, okay? Represent pulling. Okay? And here's the mass of the block. What was the mass? 20 kilograms? 40 kilograms?
20.
20.
Okay. And then the force is 40. Okay. And this pulling is making an angle at 60 degrees in the horizontal. Okay.
Oh, question. Did it matter that you put the horizontal there? Could it be right there where you have the horizontal
Yeah, but
surface?
since this is pulling from this point, it makes it easier for me to break up the vector. Because the next step for me is to break up this pulling vector into x and y parts.
Okay.
So that's why it's easy, convenient for me to put.
It's easier graphically to.
Yeah, to
Alright.
explain, right? Because if I try to do it from here, then it means I'm pulling this angle from the corner,
Mm-hmm.
which means something else, because it could cause this guy to lift up, and it just, anyways. So I go this will be my F pulling the X direction, right? And this will be my F pulling the Y direction. And remember, I can always redraw this here like this. It's F pull Y, and that way it's really clear adjacent opposite, right? Which one's sine, which one's cosine. Okay? So that's those forces from the pulling. Now on top of that, we have the force of gravity, right? And we have the normal force. Going like that. There's no friction in the first part of this, right? But if there was friction, we would put here. Okay. So we drew the free body diagram. Remember, that's the first part. Always draw the free body diagram. Next part is we want to write the sum of forces. So in this case, the sum of forces, right, in the x direction, okay? In the x direction is going to equal what? We have FPX this way, right? Let's assume this is positive x. Right, with x direction this way. And then we have, in this part we assume there's no friction, right? No friction. So, and that's just going to be MA x direction. So if I solve this for the acceleration, then my AX equals the whole force in the x direction over M. Okay? And then the sum of my forces in the y direction. Okay? In this case I have my normal force going up, right? Plus my pulling force in the y direction, right? It's going up. Minus my force of gravity. And again, we can assume that this is not pulling hard enough to pull it off of the platform. So that means there's no acceleration in this direction, right? If I solve this, I can find this for my normal force. My normal force here is then going to be Fg minus Fpy. And that's my normal force acting on the block. Now, if you guys remember, it's not required for this problem, but you remember the normal force is related to the force of friction through the coefficient of friction. So the frictional force equals mu coefficient of friction times normal force. So if we're looking for it, this would be important for us to be able to do that stuff, okay? But this problem doesn't require it. I'm just doing it for your knowledge and edification. In this part, FPX, we want to break these up, right? So we have FPX, in this case, because this is the cosine, right? Remember adjacent and opposite? So this is going to be FP as the cosine, right, of that angle, 60 degrees. And then FPY is going to be FP sine 60 degrees, okay? 60 degrees is 0.5, right? It was 40 newtons was the F pulling, right? So that means FPX is 20 newtons. Okay? So I can plug this in over here. Say AX is going to be 20 newtons divided by 20 kilograms, right? So you 1 meter per second squared. That's my AX. Okay, so that's pretty easy. Yeah. And then it says algebraically derive the acceleration in the presence of friction, right? And then the friction is like 4 newtons or something. So if that's the case, we do exactly the same thing again, but now we include this in the sum of forces. So for this second part, we say the sum of forces, okay, is going to be, in this case, is going to be FPX minus the force of friction, because the friction is acting in the opposite direction of motion. It's going to go this way, and the friction is retarding it or resisting it, okay, times mass x. So for my acceleration is now going to be pulling in the x direction minus the force of friction divided by the mass. So at this point, if you come to this point, you're in pretty good shape, right? But you can take it a step farther. You can say this is now 20. We just did that here, right? I think force of friction is 4 over 20. Okay, this is 0.8. There you go. I think that's full marks, right? Okay, so write down the equation for acceleration of the box in the presence of a frictional force of 4 newtons. So you don't actually have to write 0.8 meters per second squared. You can stop before that point. If you're right, it's not going to hurt, right? Good? So pretty easy? Especially now after you've seen it the first time, it's pretty straightforward? Yeah? You guys are so enthusiastic, it's scary. I swear to God. Other than just gravity, right? What it means to the person. In my, like for example, my 231 class, it's this kind of problem. But then on top of that, they also have to calculate how heavy the box is on the guy who's holding it. A box of medicine while these things are happening. So that additional complexity and a little more geometry, but it's not that hard. Okay, so in this problem, we have an elevator, a pulley, or a mast and a crane. Okay, and this mass is got a force acting, force of gravity, okay, and it's got a tension force. And depending on the problem, it may say I'm moving with a constant speed. So if I'm moving with a constant speed, then it's going to say V like that. If I'm moving up with a constant speed. If I'm moving down with a constant speed, then it's going to say like that. I'm just saying the etiquettes of a free body diagram, right? But on the other hand, it says, okay, I'm accelerating upwards, then I'm going to go like that. And if I'm accelerating downwards, right, go like that. Real complicated stuff. Okay. The problem here happens. This specific problem says, how much rope would be how much tension of the rope if it's accelerating vertically upwards with an acceleration of 1.8 meters per second. So this acceleration is going upwards, so it's going acceleration like this. Okay? So there we go, we're good to go. Right? So now we did the free body diagram. We're good. Now we say sum of forces. In this case, the sum of forces is what? We assume this is positive, right? So we're going to have a tension force minus the force of gravity. Okay, now, out of curiosity, What if instead I said this is positive? How would that change?
Then it will be,
If I said the direction of motion, if I say that, if I choose this as my positive direction, right? Then T is pointing in the positive direction, and FG is pointing in the negative direction, right? And A is pointing in the positive direction, right? Equals MA. But if I instead I said, no, I want to make this my positive direction, what's gonna happen?
It's just gonna switch.
Switch what?
the signs,
Of what?
uh,
In this case, if I did it like this now, it's gonna be minus T
plus
plus FG, right?
Yeah.
It's gonna be minus MA. Because A is going in the other direction. Well, but if you look at it, it's the same, right? You get my point? I was just bringing the point up just in case, because sometimes you guys get caught up with these signs, you know, so. Okay, so that means that I solve this for my tension. My tension here is gonna equal MA plus FG. So I'm literally just moving this guy over to this side. Of course, my FG is mg, right? So I have MA plus mg. Okay? And then my tension then is mass times acceleration plus gravity. And that is 200 kilograms, if I remember correctly, right? 1.8 plus 9.8, right? 10, 11.6. So 11.6 times 200, right? 11.6 times 100, 1160 times 2, 2320, 2320. Is that right? Two, three, two, zero. Woo! I'm awesome. Now, keep in mind, because it's such a simple problem, I'm going to be really critical about your free body diagram. Right? I mean, this is a short answer problem, and look at it. It's easier than most of your multiple choices. So, you know, it's a gimme. Because I've asked you to do a lot here in the rocket problem, and this is not so bad, but it's a little bit of work associated with the soccer ball. Okay. So we have a soccer ball. It's going to be kicked with some initial speed v0, initial velocity v0. Sorry, and then v0 makes an angle with the horizon. And it's gonna go up, and then hit the ground, okay? So, this guy has some maximum height, right? And it's gonna have some range, you know, maximum or distance, okay? When we do this problem though, this is a two-dimensional problem. It has a vertical part and horizontal part. If you consider this to be our x direction, right? We consider this to be our y direction. Okay? Then in that context, we have to break this into vector components. So we can take this and say, okay, this is going to be my vx part, right? 0. And this is going to be my vy 0. Okay? If I redraw this here, it's like drawing this like this. This is my vy 0. So it's my triangle. And this is my right angle right here. So, you see it? Adjacent, opposite. Adjacent cosine, opposite sine, right? Very clear? Excellent. So, the fact that these are two dimensions means that we can really break this up into two different parts, right? The x part and the y part. And also, remember what we did last time was the acceleration here is going to be, this guy is going up, but the acceleration is down, so the acceleration here is negative. And this guy's going down and gravity's down, so the acceleration is going to be positive. So what the rule of thumb we used for the rocket problem was that this should be two problems. This should be problem 1, right? This should be problem 2. And that's a rule of thumb, and it's a good rule of thumb. But in this particular case, because of the symmetry, we don't have to worry about part 2 because we'll answer it as we answer part 1. I mean, we realize we get the same answer as part 1. So in part 1 here, let's start with part 1. we look at the free body diagram. What are the forces acting on this guy? The forces acting on this guy are the force of gravity. Okay? So as it's moving up and the force of gravity is down, assuming no air resistance, right? So then we can move to the sum of forces. So the sum of forces for part one, okay? So forces in this case is going to be what? It's only force of gravity. We're going up, but force of gravity is down, so it's going to be minus Fg, right? Equals ma y, okay? Because we're talking about acceleration in the y direction, okay? So that means that ay equals minus Fg over m, which equals minus g. Okay? Great. So that's in the y direction. In the x direction, right, sum of all forces, in the x direction is what? There's no forces in the x direction, right? So 0, which equals max. So what is the acceleration in the x direction? Equals 0. Because there's no forces in this direction. Okay? So we're really good. So now we find the acceleration in the y direction, we can do the equations of motion in the y direction. Okay? So we have the Vy final equals Vy initial plus Ay times time. And we have the y final equals a y initial plus Vy initial time plus 1/2 Ay t squared. And again, these equations are given. We have the acceleration, so I can replace this, Vy final. Bless you, Matthew. Vy 0 minus gt. And this one here is y final. But we can assume this initial position is 0, right? Get rid of it. So this is going to equal Vy 0 times time minus 1/2 gt squared. Okay, so those are our simplified equations in the y direction, okay? So here, what do we know? We know the acceleration of gravity, right? We know the initial speed. This is the initial speed in this direction. We haven't calculated it yet because we have to do the sign of this number, but we know what it is, right? And we also know what the final speed in the y direction is, right? Whenever the final speed in the y direction, right, it's always going to be equal to 0 because it's, remember the motion, whenever we have this kind of motion, it goes up, stops, and falls down, remember? At that point, it's 0, so we know the speed. So we know the time, we can actually find the time it takes to go from here to there. So by doing this, we have 0 equals Vy 0 minus g times time. By bringing the g over, again, we get that same thing that we've been getting so many times, Vy 0 over g. And that is the general answer. So the time to max height, right, is Vy 0 over g. So that's how long it took to go from there to there. And we can plug in a number and everything in a minute, but that's the general form. The maximum height, though, we can get right out of this guy. So y final. In this case, we get the Vy 0, right, times time, times this time right here, which is the Vy 0 over g, minus 1/2 g times this squared, right, which is going to be the Vy 0 squared over g squared. Now this is g's cancel, right, like that. So this is Vy 0 squared over g minus 1/2 Vy squared 0 over g. So it's an apple minus half an apple leaves me half an apple, right? 1/2. This is always the case. And this is, again, a general answer. Right? So now we know the time it takes to get up here and the height it takes to get up there. But we know more than that, right? We also know that the fact that it took that time to get here, because acceleration of gravity here and here is going to be the same acceleration value. In other words, the accelerations are symmetrical. Then whatever time it took to go up is going to be the same time it takes to go down. So we also know the time of flight, right? So from this symmetry, we understand that the time of flight, right, the time of flight is going to equal two of these time and max height. 2 of the times of the maximum height, okay, which is gonna be 2 times Vy0 over G. And we'll plug in a number in just a minute. We'll plug in the number for this in just a minute, okay? So we know the first question asks us what is the, how long will it be in the air, right? Isn't that the first question? How long does the ball stay in the air? What is the maximum height above the ground reached by the ball? And what is the acceleration and magnitude in the direction of the highest point? And then how far across the field does the ball go? Okay, so if you look at this picture, we now know, right? Time of flight, Vy0. And remember, Vy0 here is the sign, so we can rewrite this if you want. It's 2V0, the sine, the angle, right? Over G. And the sine, I think the angle is 60 degrees, maybe, I don't remember. The angle is 60 degrees, and the initial speed is 25. So the time of flight, right, is equal to 2 times 25 meters per second, right? Times the sine of 60 degrees, over G, which is 9.8. What is that, 0.86 times 50, right? So times 10 is 8.6, that's 5, 400 something. And times 10, what is that, like 4.4?
Yeah, 4.4.
4.4 seconds. Okay, that's how long it stays in the air. So that's how long it stays in the air. Now when we look at this picture, we look at the acceleration of gravity, we look at the force of gravity is the same on both sides, right? So that part of the question that says to us, oh wait, we have to calculate y final, sorry. I skipped the step. Y final is, let's get 1/2, right, times 25 squared times the sine squared of 60 divided by 9.8. Okay, so that's 625, right? And then 0.86 squared. So it says 0.65. 0.65 to 625. Right. 10. So it's 625, 65, 40. So it's probably 23, 24. 23. You guys have how many calculator? Maybe 24 or something? No, 21 maybe. 21, maybe it's 22. I lost track now, sorry. Did you do it?
55? It's not 55, right?
Okay, so this is 825 times 60 sine equals square it, right? And then divide by 19.6. 23.9, well, I said 24 originally, right? So okay, 23.9 meters, okay? So that's the maximum height. So basically this answers part 1, full points, right? This answers part 2, full points, okay? The next part is looking at the symmetry between the forces of forces of gravity. They're both the same. In other words, the force of gravity doesn't change during the flight here at the maximum height or on the flight down. It doesn't change. So that's what you want to say. Is the acceleration of gravity is always down and it's always 9.8. Right? Okay? And then part 3 it says how long across the x part of the field. So now we have to do the x equations. So for the x equations we have Vx final equals Vx initial plus AXT, right? And we have x final minus x initial, which is just the distance or the range it's going to go downfield. Vx0 t is 1/2 ax t squared. So, we said that ax0 is equal to 0. So that clears this bad boy right here. It's gone. Okay. And this just tells us that the speed is constant, so we don't care. It doesn't give us any useful information. This is the distance downrange, right? This is the delta x downrange, right? Vx0 is just going to be the x component of this, right? So let's call it Vx0 for now. And the time is literally the time of flight, right? The time it takes to get down here from here is the time of flight, right? So we can just multiply by that time of flight here, right? Which was times 2 Vy0 over g, okay? And we can simplify, so we got sine and cosine, right? So we have 2 times V0 squared, cosine of 60 degrees, is the sine of 60 degrees, divided by g, right? So this distance downrange equals 25 squared. So what's this? Sine of 60. So what is that? Is that 2 cosine 60? So it's the sine. Is it the sine, cosine? Yeah, the sine of 120. So the sine 120, right? Over 9.8. Right, so that's what? 625 times, let's see. So, 120 sine, right? Times 625 divided by 9.8. That's 50. No, I did that wrong, didn't I? Or it's 60. Let me try without doing the trig, right? So it's 60 sine times 60 cosine. I screwed up. Okay. Times 625. Close. Times 2. Close. Divide by 55. I'm still getting 55. Huh? I still got 55. So I don't know. Did I ever wrong? 55 meters. V0 is 25, right? Yes. I don't know if you guys saw what I did there, but the 2 cosine sine is equal to just sine of 2 twice the angle. I cheated. But I get the same answer, so 55 meters per hour. Maybe I did something wrong. Anyways, the time it took to go from here to here is literally the time of flight, and so we said Vx times the time of flight, which is this guy, and then the final answer is 55 meters. Right? What, typical soccer field is 100 meters? Is it 100 meters?
I'm not sure.
100 meters seems a little big.
Check.
I'm kidding, you don't have to look it up.
You sure?
I'm just thinking if it is 100 meters, then the fact that he kicked it like that barely makes it past midfield, You don't look happy.
I'm tired.
But are you following?
Yeah, I'm fine.
Okay.
Although, actually, I don't, wasn't getting 55 minutes. Like, I don't know how.
Wait, say that again?
Like, I wasn't getting, like, your final answer for the.
This one?
Yeah. I kept on trying to put in my calculator and I don't know.
Are you
if the way
in
that-
radians or degrees?